Let's solve one question which is about related rates. A kite 100 feet above the ground moves horizontally at the speed 8 feet per second. At what rate is the angle between the string and a horizontal changing when 200 feet of string has been let out? Let's draw the scenario. We have a ground and we have a kite moving horizontally above the ground, and we know that this is 100 feet. Now we have to draw a string. That's me. Let's say that's me holding a string, and of course the string I have to let out longer and longer, and this will be my angle of elevation, the angle between the string and the ground. Okay? But what I will do, I will draw just one nice triangle for my model. That's the kite, that's 100, and since the kite is flying, moving, we know how this distance, which I can project this distance down, is this one. We know how this distance is changing. That means the rate of change of x with respect to time, it's 8 feet per second. That's how this distance is changing. And we have to find out how the angle is changing, d theta, dt, how angle is changing with respect to time at the moment when this distance, I can call z. If z is 200 feet. When z is 200 feet, like let out. But we have to remember that this is not really 200. It's just the one moment at the time. We will use 200, but just at the end. That's me looking at my nice model, nice triangle. I have to have the relation between x, theta, possibly z, and 100, because 100 is not changing. The kite flies horizontally. And since I see the right triangle and the angle, the trigonometric ratio are the best. And I will say I have to involve 100 and x. That's mean tangent theta, which is opposite over adjacent, or cotangent theta, adjacent over opposite. And I think in this case I will pick cotangent since x is on the top and it's just the linear relation. Let me do one thing. I will multiply both sides by 100. That means I will have x equals to 100 cotangent theta. That means this is good relation. Now I need the relation between the rates. I will differentiate. Derivative of x is dx dt with respect to time. Copy 100. Derivative of cotangent is negative cosecant square theta times d theta dt. Okay. That means now after the derivative I can substitute everything what I have. The rate of change of x with respect to time, it's 8. This is 100. I can place that negative in front. Cosecant square theta, it's 1 over sine theta squared. And the rate of change of angle we actually looking for. We will need to have sine theta. If I will draw a triangle one more time, okay, this is x, this is 100. And we're looking for the rate of change at the moment that this is 200. And we can nicely see that I can read a sine theta ratio, which is 100 over 200, of course, is 1/2, and the reciprocal of this cosecant theta is just 2. That means let's just substitute 8 negative 100 2 squared d theta dt. Let's divide my slide. Okay, and now what we have? We do have 8. Negative 2 squared is 4. 400 d theta dt. Dividing by negative 400, both sides, I will have my answer. And 8 divided by 40, it's simply 5. 1 over negative 50. The rate of change of angle, it's negative 1 over 50, and the units for angle is radians over second. This is the final answer. And that means please make sure that you understand each step, and especially the relation. Always be wise and make pick the easiest one. In this case, I did pick cotangent, since it's much easier to differentiate x to the power of 1 rather than